in this lecture we shall be discussing on some of the bus standards and protocols which are used inside a computer system, not necessarily only for interfacing the peripheral devices, but say the bus that exists between the processor and the memory, that also we will be looking at the overall picture first, and then we shall be looking at one very popularly used bus standard, namely the USB, and go into some detail there exactly what it is about. So, the topic of today's lecture is bus standards. Now, let us start by defining a bus. Well, a bus roughly refers to a common shared path. Now, in a city when you board a bus, you see the bus takes a group of people from one point to the other. So, it is like a common shared path, many people are using the same communication facility, unlike a private car which is dedicated to a person, right. So, a bus by its definition means a common shared path which can be used by more than one entities for communicating between two endpoints. Okay. So, basically the bus is a collection of wires. Well, as this diagram shows, you can have your CPU, your memory and some secondary, some I/O, let us say disk. This is a simplified diagram and this is your bus. This will be a collection of wires and connectors. Through this bus, data will flow. Now, in this bus, so what are the basic things that should be there? Well, of course, there should be the address lines. So, when the CPU is sending some data, CPU should also mention that to whom that data is meant, because there can be multiple devices on the bus. So, the address of the device. Then of course, the actual data. So, how many data can be sent at a time, it depends on the width of the bus, how many wires are there. Then there can be some control signals. The control will tell you exactly what kind of operation CPU is trying to do. So, whether the CPU is trying to read the status of the device or wants to send some data or receive some data and so on. And in addition, there can be a set of power supply lines, various voltages, ground, so that some of the devices that are connected, they can directly draw the power from those lines. So, the most important lines in the bus, of course, controls are also important, it is address and data, because address will specify the destination. So, with whom the master is wanting to talk, and data bus will carry the actual data, right. Okay. So, let us look at some of the terminologies now. Well, when we say bus protocol, what does it mean? Well, protocol, if you look at the dictionary meaning, protocol is a set of rules or conventions which both the end systems should comply or follow, so that faithful communication can take place. Similarly, in a bus or for any communication system, there has to be a protocol. Both the end systems should be following the same set of rules, so that data communication can take place without any problem. Okay. So, bus protocol essentially constitutes the rules that determines the format and transmission of data through the bus. Now, the bus can be either parallel or serial. For a parallel bus, the idea is that data are transmitted in parallel, means I can have 8 or 16 or 32 parallel lines in the bus through which data can be transmitted multiple bits per cycle. This is meant by parallel. Okay. So, of course, the advantage here you can see is obvious, because there are so many lines with which data can flow, it is fast. But the disadvantage is that your cable or the bus will be very thick, there will be so many wires. So, for a long distance communication, the length of the cable will be large, the cost of the cable will also be higher, and because there are large number of lines that are packed in the same cable, there can be inter-line interference particularly when data communication is taking place at higher frequencies. Because of this, parallel bus cannot be used for longer distances. So, in fact, you see that most of the communication that we carry out today are based on some kind of serial bus. So, in our earlier systems like that printer port I talked about, some parallel bus standards were there, but today you will find very few. Okay. All right. So, in contrast, the serial bus can have a single line for sending and a single line for receiving. So, when you have a single line for sending, then you can have that serial communication protocol I talked about earlier using start bits and stop bits to synchronize between the sender and receiver. That kind of a format can be used. Well, there are other ways also, some synchronous kind of communication can also be done, where the sender and receiver knows the exact speed of data transfer. Those are also possible. Okay. So, because the number of lines are very few, the advantage is that the cost of the cable will be very low. So, for long distance communication it will be very suitable, and because there are very few lines, interference will be very less. But disadvantage is that because you are sending the data serially bit by bit, it will be relatively slow as compared to the parallel bus. Okay. So, in a bus, so as I said, there can be many nodes or devices connected to it, like let us say here we have a bus, we denote the bus like this. There can be several devices which are connected to the bus. The devices may not all be of the same type, they can be different. One can be more powerful, one can be very simple. Just I am calling them D1, D2, D3 and D4. Now, by calling them as master and slave, what I mean to say is that suppose D1 and D4 wants to communicate. Now, depending on the bus protocol and the capabilities of these device interfaces, there can be a scenario like this, where this device D1 will be designated as the master and D4 will be designated as the slave. What does this mean? That D1 being the master will be able to initiate the data transmission, but D4 on its own, because it is the slave, it cannot initiate. The master is always responsible for initiating every data transfer over the bus. So, there are many protocols where there is a master slave relationship between the various devices, and it is the master which takes care or initiates the communication with the other devices which are slaves. Okay. Now, the buses that exist inside a computer system, now we are talking about a bus or the buses which are there inside a computer system. If you just open your desktop or a laptop, you will see a lot of circuitry inside, but schematically or architecturally, how does the devices get connected inside there, say on the motherboard. So, here we are talking about that. So, local or system bus, this is the term we use to refer to a bus that connects CPU and memory. Now, you know that in a computer system, the CPU and the memory are the fastest two components, and the communication between CPU and memory is the most crucial in determining the overall performance of the system. Okay. So, this bus that connects a CPU and the memory is referred to as the local bus or the system bus. Well, following the nomenclature of Intel, we can distinguish the buses as front side or back side. Front side bus means the bus that connects CPU to the other components. This was the original concept, earlier concept. Okay. But if you look at the modern motherboards, the CPU, the way they are connected on the PCs and the laptops, This is with respect to the modern Intel architecture for the motherboards. Here front side bus refers to a bus that connects CPU to the north bridge chipset. So, here we are talking about a connection like this. There is a CPU, there is something which is called north bridge, and the CPU is connected to the north bridge by a bus which is a high speed bus, and north bridge may be connected to various high speed devices like memory. Memory is one example. There can be others. Okay. So, there can be a backside bus which can connect the CPU to the level 2 cache if it is outside the processor, or level 3 cache, and there can be a memory bus which connects north bridge chipset to the memory. So, here this link I talked about, north bridge is connected to the memory, this is the memory bus, right. So, there are different kinds of devices which are connected to there. There can be a backside bus also where the CPU is connected to L2 or L3 cache, that bus is also there, L2 or L3, depending on whether L2 is inside the CPU or outside. Okay. Fine. And you have a AGP bus. Well, AGP bus refers to the bus through which the graphics cards are connected. So, here the north bridge chipset is connected to the GPU. So, here there is one connection with the north bridge that connects with the graphics processing unit GPU. So, this bus is referred to the AGP bus, right. And in addition, there are several other buses inside the CPU. So, there is another device there which is called the south bridge, that is also there. The north bridge is connected to the south bridge, and the south bridge is relatively much slower in speed. South bridge typically connects devices which are not that high speed. Okay. So, this architectural wise, you can see there are so many buses inside the systems, and the devices are connected to one or more of these buses. Now, talking about some of the standards which evolved over the years, these are standards through which you can connect some peripherals to a computer systems. It can be motherboard, it can be some connectors that are connected to the motherboard. Well, ISA, PCI, FireWire, PCI Express, and today you have USB. These are all examples of some bus standards which connects peripherals to the motherboards in some way. They vary in their speeds and other capabilities. Okay. Fine. Now, let us look at a typical architectural diagram of a motherboard inside a PC, a modern day PC. This will give you a fair idea. Well, at the top I am assuming that this is a dual core processor. There are two cores which are shown here. You see, there is a 3800 megahertz core, the core is running at 3.8 gigahertz. There is another core, and inside the core, inside the chip, there is a 2 megabyte cache. This is the L1 cache, let us say, right. And here you can see is the north bridge. Now, you see, I am not sure you have you have noted or not. So, when you buy a computer system, or when you look at the specification of a PC, when you just want to buy, you will see that it does not only talk about the processor and the clock, it also uses a code name for a chipset. It uses Intel this chipset. Chipset actually refers to the north bridge and the south bridge combination. What are its capabilities, what are its speeds, and so on. Okay. The chipset will determine that. So, this north bridge and south bridge taken together, this is the chipset we can refer to. So, you see north bridge how it is connected. So, on one side it is connected to the cores, the processors. This is a high speed bus, as you can see this runs at 1066 megahertz. So, it is about 1 gigahertz speed, and the speed of this bus, the data bandwidth is about 8528 megabytes per second. So, it is pretty fast. North bridge connects to main memory via the memory bus. Memory bus, well, in this example, so it is running at 533 megahertz and it can transfer data 4264 megabytes per second. Okay. This is DDRAM, 533 megahertz DDRAM. So, on the other side of the north bridge, through the AGP bus you have the graphics card or the GPU can be inside. Okay. And north bridge is connected to the south bridge through a relatively lower speed link, this is 100 megabytes per second. Now, south bridge connects to the other devices, like it can have a IEEE 1394 interface, which is sometimes called FireWire. Of course, now FireWire has become obsolete. In the modern computers you do not see FireWire anymore. So, you can connect some devices like CD-ROM, DVD through this. So, you can have a network adapter card, Ethernet interface, that also can be connected through it. So, you can have these slow systems like keyboard and audio, this can have a much slower bandwidth. So, you can have a hard disk connected through either IDE interface or SCSI interface, SCSI, or here you can have USB interfaces where you can connect various sorts of devices. Well, now the point to note is that in the modern systems, as the standards have evolved, this USB standard has become more and more widely used and faster. So, there are USB versions which instead of being connected to the south bridge, they are connected directly to the north bridge because of their much higher speeds, right. So, just architecturally this is what that exists inside a CPU motherboard, and you can see there are so many different buses that exist there, and each of these bus will have their protocols, their rules. So, we are not going into the detail of all the buses, rather some of the basic concepts I will try to highlight, which will be common to most of these buses. So, talking about a bus, some of the characteristic features will be bus width, meaning how many data lines are available. So, how many bits of data you can transfer in every cycle, and the speed of the bus or the bandwidth. So, total amount of data in bits per second or bytes per second that can be transferred over the bus, right. Now, let us look at these features, bus width and bandwidth, for some of the commonly used bus standards. Well, some of the bus standards were used, now you cannot see them anymore, they have become obsolete. You see, the ISA bus was a 16-bit bus which carried 16 wires and the bandwidth was 15.9 megabytes per second. This was extended ISA 32 bits, 31.8, just double. PCI was also 32 bits, but the speed was about 4 times. Then 64-bit PCI came, version 2.1, where the bus width was 64. So, the speed was again increased significantly, 50. So, you see these parallel buses, they exist more inside a system within the motherboard, but today when you connect an external peripheral with the computer, because of the cost of the cabling, the data communication is mostly serial in nature. But inside the motherboard, as you can see these buses, they are all carrying 16, 32, 64, many bits in parallel at a time. Okay. And for the graphics AGP bus, 32 bit, but it runs much faster, 2133 megabytes per second. But USB 2, well, this is an old standard. There are newer standard we will see later, USB 3, 3.1. Here data communication is serial and the data communication speed can be in one of three modes, slow, full and high. So, in the high speed mode it can go up to 480 megabits per second, but nowadays with the modern USB versions you can go up to several gigabits per second also. So, it is pretty fast. So, FireWire was supposed to be one of the fast standards. This is also serial, this can go up to 400 megabits per second, and PCI Express is one of the fastest buses available. It carries 16 wires and the speed is 8000 megabytes per second. Okay. So, just to have an idea. Buses can also be synchronous and asynchronous. I will take an example to illustrate the difference between synchronous and asynchronous. So, with respect to IO transfer you have already seen. So, the concepts are very similar. For a synchronous bus, there will be some kind of a common clock between the sender and the receiver that will synchronize all data transfer operation over the bus. Now, in contrast, an asynchronous bus does not have any common clock, and just like in asynchronous IO we had to use handshaking, here also there will be a number of handshaking signals which let us say the master and slave will be sending each other, so that the data communication can be completed and both sides will be knowing about it. Okay? Fine. So, let us take an example. This is an example of a bus that connects CPU and the memory. So, the first example we take is that of a synchronous memory read. So, here we are showing some signals, timing diagram. First one shows the clock and these are the clock states T1, T2, T3. This is the address bus, data bus. These are two control signals, memory request and read. So, first step is CPU places the address of the memory location on the address lines. It is here in the first clock. So, after the clock rises high, there will be some delay. So, after that delay here, this part, the valid address, CPU puts the address of the memory location on the address line. This is the first step. See here, during this time none of the memory request and read lines are active. These are bar, means they are active low, they will be active when they are put to low or 0. So, first step is to put the address. Then after the address is put, second step is CPU will assert the memory request and read lines. So, it will set its here, memory request line will be set to low, read line will also be set to low. So, that the memory system will now know that it is a memory request and the CPU is requesting a read. So, it is here. So, at the end of T1 these two signals have been asserted. This address is already valid. Okay? Fine. Third step, memory controller will be accessing memory location and load the data on the data lines. Now, memory will be having some access time. Let us say the read signal was activated here, it will take so much time and it is here when the valid data will come on the data bus. So, you are giving sufficient time for the memory to access the contents. Okay. So, the data will be loaded on the data line here somewhere in T3 out here. Now, when the data has already arrived, so the last step will be the CPU will be reading the data because it is already on the data line and it will deassert memory request and read lines because it is already done. So, memory request will again be set to high, read will again be set to high. So, this is synchronous because CPU knows exactly how much time memory will take to read the data. So, it is waiting for exactly that much time, it will expect that data is already there, it will read from the data bus. So, this is what is meant by synchronous interfacing. So, just to recall, CPU puts the address on the address bus, it activates read and memory request signal. Because it is synchronous, it knows exactly how much time memory will take. So, just after that much time it reads the data from the data bus and again deasserts memory requests and read. But for asynchronous interface, CPU may not know in advance exactly how much time memory is taking. So, there has to be some signal back from the memory indicating that well data transfer or memory access is complete. Let us see. So, the second example that we take here is that of asynchronous memory read. So, here you see, so again in additional to the address and date, you see here because it is not synchronous, I am not showing the clock signal, because earlier everything was happening in synchronism with the clock. So, we were assuming both the CPU and the memory system were having access to the same clock, but for asynchronous system here we are assuming that there is no clock, there are other handshaking signals using which the CPU and the memory both will be knowing exactly what is going on. Let us see. So, there will be address lines, data lines, and there are some other signals you see memory request, read, this msyn and ssyn, these are synchronization signals. Let us see. So, how these are how this work. So, the first step as usual will be for the CPU to put the address of the memory location on the address lines. Let us say it is here. So, it is here, the CPU is putting the address on the address bus. So, the valid address is available on the address lines. Second step, well after the address line have become stable, this symbol means it has become stable, it is here stable. CPU will assert memory request and read lines. These are two signals which CPU is sending to the memory system. So, memory request line is activated, read line is activated. So, this will be after a little delay after the address lines have been stabilized. So, once these two have been activated, now memory read process starts. Third step, what will happen? CPU will assert the msyn line. So, after memory request and read, now msyn, this is a handshaking signal. This msyn will tell the memory system that CPU is now expecting some data from the memory. This msyn is a signal which is generated by the CPU, right. So, it is asserted after memory request and read are asserted. Then memory controller will take some delay depending on the access time, this can be less, that can be more. So, it is not fixed. Load the data from the data line. So, after some delay the data will come on the data line, and once it is valid, the memory controller will activate the ssyn. So, ssyn is a signal that comes from the memory controller to the CPU, and the CPU when it sees that ssyn is activated, so it will know that well data is now available on the data bus. So, now what the CPU will do? CPU will read the data from the data bus and it will deassert memory request, read and msyn, and lastly memory controller will deassert ssyn after all these lines have done, indicating that the operation is over. So, essentially in this method if you see, so you have the CPU, you have the memory system. So, actually the memory controller is interacting. So, you have just for memory read I am saying the signals which are used are memory request, read, then there are two handshaking signals, CPU is sending to memory the msyn signal and memory is sending back to the CPU the ssyn signal. So, using these handshaking signals, data transfer can take place even without CPU and memory sharing a clock. So, there is no clock sharing, this is the point to be noted. Right. Okay. So, today, as I have given the example of that Intel motherboard, bus architectures are typically based on the bridges, this bridge concept, the bridge concept which Intel had proposed. So, many of the other manufacturers are also going by that. So, here system includes a lot of buses that are not all connected together, they are segregated by bridges. Like you recall, I mentioned the north bridge will be connecting RAM, memory, video card, AGP, PCI Express, the higher speed buses. The south bridge will typically connect the PCI, which is a lower speed PCI, clock, USB and other devices like keyboard, disk, etc. So, Intel and also other companies have started following this kind of bridge based bus architecture. So, this is the diagram which we showed earlier. This is an example of a bridge based bus architecture, north bridge, south bridge. This is a very commonly used architecture which is available in the desktops and laptops that we mostly see today around us, right. So, with this we come to the end of this lecture. So, in this lecture we have talked about the need of the buses inside a computer system, why we have so many different buses, because each bus has a specific requirement, their speeds can be varying widely. So, instead of all devices connected to the same bus, it is always better to segregate the buses, and by isolating them using bridges you can have a better management. So, in the next lecture we shall be looking at one specific bus standard in some detail, which is really becoming universal in today's context, that is the Universal Serial Bus or the USB. Thank you.